Hello friends, in this video we'd like to solve the following problem from the Romanian National Mathematical Olympiad for 12th graders 2022, problem number 2. We wish to find all unital rings A such that A cubed is either 0 or 1 for all elements A of our ring. It's a very nice algebraic problem, and here are my hints. First, show that in our ring it's of characteristic 2, so 1 plus 1 equals 0 in our ring by considering minus 1 cubed. Second, consider a plus 1 cubed and show that a times a plus 1 is either 0 or 1. Now, show that if a times a plus 1 is 0, then a is either 0 or 1, which means that if a is not 0 and if it is not 1, then a times a plus 1 must be equal 1 for all elements A which are not 0 and 1, as I said. Which means that our ring is a division ring, by the way. Now, show that this condition. You should consider A and B, which are in elements of our ring but not 0. You should consider A plus B squared. By considering this expression, show that either a plus b is 0 or 1, or ab plus ba is 1. And show that the last possibility is in fact not possible. So if a, b, and a plus b are not 0 and not 1, then ab plus ba cannot be equal 1. It's impossible. And deduce that we have only two possibilities. Either our ring is isomorphic to field F2 or to field F4. So give this problem a try, and I will see you in just a minute. Alright, so let's start. I will proceed by proving several claims. My first claim is that for every or that 1 plus 1 is 0 in our ring. Proof. Notice that, well, let's consider minus 1 cubed. Minus 1 cubed is minus 1, and we know that it's 0 or 1. Well, it's not 0 because we suppose that our ring is unital, so 1 is different from 0. So since 0 is not equal 1 in our ring, we have that minus 1 equals 1, i.e. 2 equals 0, so 1 plus 1 is 0, which closes the proof of my first claim. My second claim is that for every element of our ring, a times a plus 1 is 0 or 1. Either 0 or it is 1. Let's prove it. Well, let's consider a plus 1 cubed. A plus 1 cubed can be written as a cubed plus 1 plus 1 plus 1 a squared, a bit artificially, but I will write it as it is, plus 1 plus 1 plus 1 a plus 1. But notice that, well, 1 plus 1, as we know it, by claim number 1, is 0. So this can be simplified, and we get that a plus 1 cubed minus a cubed equals, and minus 1 equals a squared plus a. But notice that this is either 0 or 1, this is either 0 or 1, this is 1. So this entire left hand side is either 0 or 1, because remember that 1 plus 1 is 0. So the entire left hand side is either 0 or 1. And on the right hand side we have a times a plus 1, which is exactly what we wanted to prove. My next claim, my claim number 3, is that for every element A which is not 0 and which is not 1, in fact, A times A plus 1, or maybe let's write it as A squared plus A, it must be equal 1. It cannot be 0. Let's prove it. Let's prove. Suppose that A squared plus A is 0, because it's either, by claim number 2, it's either 0 or 1. Suppose that it is 0. Then, what do we have? Then, A cubed plus A squared is also 0, but A cubed is either 0 or 1. Or maybe, yes, it's either 0 or 1. So, A cubed, let's write it, it's either 0 or 1, so A squared, but A squared, notice that A squared equals minus A, but minus A, or maybe, you know what, let's write it like that. A is the same as minus A. By this equation, minus A is A squared. By this equation, it's the same as minus A squared, so it's A cubed, and A cubed is either 0 or 1. So we have proven. I'm juggling with these minuses because 1 equals minus 1 in our ring. So we have demonstrated that A is either 0 or 1. So by taking, by the law of contraposition, we have demonstrated that for every element A of our ring, if A squared plus A equals 0, this implies that A is 0 or 1, which is equivalent to our claim. It is exactly equivalent. All right, my fourth claim. My fourth claim is what exactly? Yes, I wish to prove, I will prove that for every A, B, which are numbers, elements of our ring, but not 0 or 1, either A plus B equals 0, or A plus B equals 1, or AB plus BA equals 1. And let's prove it, because we are getting closer and closer. We are knowing more and more about our ring. Proof. Suppose that we have elements AB of our ring, and let's suppose that this is not the case, and this is also not the case. So suppose that A, B, and A plus B are elements of our ring, but not 0 and not 1. Now, it's time to use claim number 3. By claim number 3, I know that A plus B squared plus A plus B, well, it cannot be 0, it must be 1. And let's expand it. Here we have A squared plus AB plus BA plus B squared plus A plus B equals 1. And now I will use claim number 3 once again. A squared plus A is 1. B squared plus B is also 1. So let's write 1 plus AB plus BA plus 1 equals 1. Again, by claim number 3. But 1 plus 1 is 0, so we have AB plus BA equals 1, which closes the proof of my fourth claim. Alright, and now, my last claim probably last, we'll see, is that for every two elements A and B, well, the last, it's not possible. It's either A plus B is 0 or 1, or AB, or maybe, you know what, no, let's write it like that. But for every AB in our ring, which are not 0 and not 1, either A plus B is 0 or A plus B equals 1. So it's strengthening the claim number 4, because now I claim that the last part is in fact impossible. Proof. Let's prove it. Let's prove. Let's suppose to the contrary. Suppose to the contrary that A, B, and A plus B are in our ring, but are not 0 and are not 1. By claim number 4, it must be the case that AB plus BA, it must be equal 1. But now, let's take this equality. And since this is the case, now we can see that AB equals 1 plus BA. I'm adding BA to both sides. And now, again, BA is the same as minus BA, so I can write it like that. And now I will do what exactly? I will now take this equation and I will multiply on both sides by AB. All right, and what do we have? We have a squared, b squared equals ab plus ab. All right, but now let's notice that what is ab plus ab? It's either 0 or 1. It's either 0 or 1. So it's either 0 or 1. Let's consider these two cases separately. Can it be 0? Notice that if, or maybe if AB plus AB is 0, well, this implies that AB is either 0 or 1. How do I know it? By one of my claims, namely, it's the result of claim number 3, probably. Yes, it's of claim number 3, because 1 happens only for elements which are not 0 and not 1. Alright, let's consider these two cases, because you know what? AB times AB is AB squared. Let's consider these two cases separately. Well, if AB equals 0, well then BA equals 1. Yes, I'm taking this line right here, and then BA must be equal 1. But now it's problematic, because if we take this line, this implies that BA, after taking square on both sides, is also 1. But here is the problematic part. Here is AB. B, 0, A equals 1, 0 equals 1. Contradiction. It's a contradiction. So it's impossible. And now let's consider second case. If AB equals 1. If AB equals 1, then, well, in the same vein, BA must be equal also 1. Because if BA equals 0, we can do the similar thing as done above. But then, what is AB plus BA? Well, it should be 1, but at the same time it's 1 plus 1. But 1 plus 1 is 0. Yet another contradiction. Yet another contradiction. So it is not possible. Alright, so remember that it was all about the right hand side of this expression. It cannot be 0, so it must be 1. So if ab plus ab squared equals 1, notice that then it should be the case that a squared b squared equals 1. But this, we can take this line right here and we can multiply by ab. And we have a cubed b cubed equals ab. Alright, but remember that by our assumption a cubed is either 0 or 1. B cubed is also 0 or 1. So product of two such numbers is again either 0 or 1. AB is either 0 or 1. But notice that now the same will happen as was above. If AB is 0, then we can get this contradiction. If AB is 1, then we get this contradiction. It has been seen before. So both this leads again to contradiction. Contradiction as above. It's impossible. Alright, so all of that leads us to a contradiction, so we have proved our claim. We have proved our claim. It was claim number 5. Yes, because we have assumed to the contrary that it is not the case. We have used previous claim and we have reached 3 different contradictions. As a corollary of claim number 5, well, if A, B are two elements of our ring, which are different, if they are different, they must differ by 1. So B equals A plus 1. Alright. But now, notice that this is about any two elements A and B. So now let's consider two cases. Case number 1. Case number 1, well, if our ring has only two elements, 0 or 1, well, then this is obviously a solution. Then A satisfies our conditions. Why is that? Well, because 0 cubed is 0, because 0 cubed is 0, 1 cubed is 1. So it's a unital ring, the simplest unital ring. Case number 2. Well, if there is A which is not element of our ring, then what happens then? Then we have A plus 1 as well. Then A plus 1 is also element of our ring. It's not 0, it's not 1, and it's not A. I claim that there is no more element. Because notice that if B is also in our ring, it's also not 0, not 1, then B is either equal to A or equal to A plus 1. So there can be no fifth element. So the cardinality of A equals 4 in this case. So our ring consists of elements 0, 1, A plus 1. And, well, this is the field with 4 elements. So we have exactly 2 solutions, up to isomorphism. So these solutions either our ring is isomorphic to F2 or our ring is isomorphic to F4, filled with 4 elements. And this closes our proof. This closes our solution, rather. So yes, thank you very much for watching. I hope that you were not lost in my reasoning. That problem was a bit convoluted. And yeah, thank you for watching. I will see you next time. Goodbye.